Alright, in this video we'll be looking at the problems from section 7.3 on equilibrium. We'll begin with problem 7.21. Which of the following statements are correct at equilibrium? Which of the following are correct at equilibrium? So, A, the concentration of reactants is always equal to the concentration of products. Say concentration of reactants equal to concentration of products. And this is false. That at equilibrium, it's the reaction rates, the forward and reverse reaction rates that are equal, whereas the concentrations of reactants and products do not have to be equal. Rarely they will be equal, but not always, far from it. So B, no reactants are converted into products. And this is also false, because when we're at equilibrium, we still have reactions taking place. It's just that we have as many forward reactions as we do reverse reactions. And so when we say no reactants are converted into products, that is false, because some reactants will convert to products, but we have just as many products converting to reactants. So the rates of the reactions will be equal. And C, the rate of the forward reaction is equal to the rate of the reverse reaction. And this statement is true. So A is false, B is false, and C is true. If you look at 7.22, it's the same question: which of the following are correct at equilibrium? A says that the forward and reverse reactions stop. Now this statement is false. The forward and reverse reactions continue to go, except that the rate of each reaction is equal. So we have a dynamic equilibrium, that the reactions still go forward and backwards, but the rate of the forward and reverse reactions are the same, so that the overall change in concentration is zero, but the reactions still occur. So B, the concentration of reactants and products does not change. This statement is true, that at equilibrium, that because the rates of each reaction, the rate of the forward reaction and the rate of the reverse reaction, cancel each other out, that means that the total concentration of reactants and products will not change. Because for every reactant that becomes a product, we have a product that becomes a reactant. And so even though they can move back and forth, the total amount of each will not change. So C, the rate of the forward reaction is greater than the reverse reaction. And this statement is false. The rate of their forward and reverse reactions are equal. One is not greater than the other, one is not less than the other, they are equal. So anyway, moving on to 7.23. It says, balance the chemical equation and write the equilibrium constant expression. Okay. So our chemical reaction that we're looking at in 723 is CH4 plus H2O, so methane plus water reacts to form hydrogen gas plus carbon monoxide. So we have 1 carbon, 4 hydrogens, 2 more hydrogens, 1 oxygen. So we need to balance this equation. I think we can do that by saying 3 molecules of hydrogen gas, because now this gets us to 6 hydrogen atoms, and 1, 2, 3, 4, 5, 6 hydrogen atoms on the other side, 1 oxygen atom on each side, 1 carbon atom on each side. So I think this is the balanced equation. And so in order to write the equilibrium constant expression, remember that KEQ equals the concentration of the products over the reactants. So that would be the concentration of the hydrogen to the third. Because of this 3, we have to take that to the power of 3 multiplied by the concentration of carbon monoxide. So those are the products all over the reactants. So CH4, our methane, multiplied by the concentration of water. And this will be equal to the equilibrium constant, the KEQ. So 724 asks us to do the same thing, balance the chemical equation and write the equilibrium constant expression, but it asks for this reaction between hydrogen gas and nitrogen gas to form hydrazine into H4. So again, our KEQ will be equal to the products divided by the reactants, and in this case our products will be this N2H4. But first we need to balance this equation. We have 2 nitrogens on our left side, 2 nitrogens on the right side. We have 2 hydrogens on the left and 4 hydrogens on the right. So we need to multiply our hydrogens here by 2. So now we have 1, 2, 3, 4 hydrogen atoms and 1, 2, 3, 4 hydrogen atoms, and now this should be balanced. So our KEQ will be equal to the concentration of the products. In this case, that would be the hydrazine, N2H4, divided by the concentration of the reactants, which in this case is our nitrogen multiplied by hydrogen, but we have this 2 in front of the hydrogen here, and so we have to square our hydrogen concentration. So it becomes N2H4 over N2 times H2 squared. (725) asks us to do the same thing, balance the chemical equation and write the equilibrium constant expression. But now our reaction was between SO2 plus O2 yields SO3. So we need to balance this equation. We have 1 sulfur on each side, but we have 4 oxygens here, 3 oxygens here. So we need to increase the number of oxygens. Let's say we have 2 sulfur trioxide, which means we need 2 sulfur dioxide, and now we have 2 sulfur atoms on each side, plus 4 oxygen, 2 oxygen. This gets us 6 oxygen atoms. 2 times 3, 6 oxygen atoms. This should be a balanced equation. So our KEQ, our equilibrium constant, again, that's equal to the concentration of the products divided by the concentration of the reactants. So our products, SO3 squared, because of this 2, all over SO2 squared because of that 2 times concentration of oxygen, O2. So this would be the equilibrium constant for this equation. Fit one more, 726. Balance the chemical equation and write the equilibrium constant expression. CS2 plus H2 yields CH4 methane plus hydrogen sulfide, H2S. So here we have 1, 2, 3, 4, 5, 6 hydrogen atoms versus 2 hydrogen atoms. But we have 1 carbon and 2 sulfurs. We have 1 carbon and 1 sulfur. So we'll need to increase the we need 2 H2S, so this gives us 1, 2, 3, 4, 5, 6, 7, 8 hydrogens total. So then 4 H2, so now we have 1 carbon atom on each side, 1, 2 sulfur atoms, 8 hydrogen atoms, 1, 2, 3, 4, 5, 6, 7, 8. I think this is balanced. So our equilibrium constant, we take our products, the methane, CH4, multiplied by hydrogen sulfide, and we divide that by our products, or our reactants, CS2 times H2 to the 4th. And we need that 4th because of this 4. We need this squared because of that 2. Okay. So 727 says write the equilibrium constant expression for each reaction. In part B, H2O is a solvent. So part A. Carbon as a solid plus CO2 as a gas yields carbon monoxide as a gas. So our equilibrium constant, see, first is this, we need to balance this. I need to put a 2 in front of the carbon monoxide. So now we have 1, 2 carbon atoms, 1, 2 oxygen atoms on each side. So everything should be balanced. KEQ equals products over reactants. So CO, carbon monoxide, squared. Now, remember, we don't include solids in our equilibrium constant. And so this solid carbon here isn't included. So we only include the CO2. So our equilibrium constant is carbon monoxide squared divided by the concentration of carbon dioxide. CO squared over CO2. And that's part A. Part B. NH3 aqueous plus H2O liquid yields NH4 plus aqueous plus OH minus aqueous. So we have ammonia reacting with water to form ammonium and hydroxide. So it's an acid-base reaction. But we remember this water is the solvent, and we don't include solvents in the equilibrium constant. So the KEQ becomes products over reactants. So our products are NH4 plus times OH minus, because these are the products, divided by NH3. We don't include the water because the water is the solvent, and the concentration of the water will barely change during this reaction, so we don't have to include it. So 728 asks us to do the same thing. Write the equilibrium constant expression for each reaction, and in part B, water is the solvent. So part A. PCl5, phosphorus pentachloride, as a gas is in equilibrium with phosphorus trichloride, also a gas, plus Cl2, chlorine, as a gas. So PCl5 is in equilibrium with PCl3 plus Cl2. So this is a balanced equation, 1 phosphorus on each side plus 5 chlorines on each side. The KEQ is equal to the products divided by the reactants. So PCl3 times Cl2 all over PCl5. So this is the equilibrium constant for this reaction. In part B, H2SO4, sulfuric acid, aqueous, plus 2 H2O liquid yields 2 H3O plus hydronium, and that would be aqueous, plus SO4 minus, well, SO4 2 minus aqueous. And so our equilibrium constant is again products divided by reactants, H3O plus squared, because of this 2, multiplied by sulfate, SO4 2 minus, all over H2SO4. Remember, water is the solvent, and we don't include solvents in our equilibrium equation. So we just have the hydronium, the sulfate, and the sulfuric acid. So 729. Explain why the concentration of solids do not appear in equilibrium expressions. This is because we only include concentrations that can change. And the concentration of a solid does not change. It is related to its density which will not change very much. And related to 729 is 730. Explain why the concentration of solvents do not appear in equilibrium constant expressions. And again, we only include concentrations that can change during a reaction. Solvents have a much higher concentration than other reactants or products, and this concentration barely changes during the reaction. So that's why we don't include solids and we don't include solvents in our equilibrium reactions. Okay, so 731. Write the reaction equation from which each equilibrium constant expression is derived. Assume that no solids or solvents are present. And this is a necessary assumption because solids and solvents will not appear in the equilibrium constant equation. And so we wouldn't see them, we wouldn't know to include them. So part A, KEQ equals NOCl squared over NO squared times Cl2. Well, we know that this is our product over our reactants. So we'll begin with the reactants. We'll say NO plus Cl squared. And we have to include this 2 because it's NO squared here. 2NO plus Cl2 is in equilibrium with our product NOCl, and we have 2 NOCl, and we'll just check. We have 2 nitrogens, 2 nitrogens, 2 oxygens, 2 oxygens, and 2 chlorines and 2 chlorines, and so this equation is balanced. Part B, KEQ equals HBr, hydrobromic acid, squared over H2 times Br2. And so our equation will be hydrogen gas plus bromine gas in equilibrium with HBr, and because of this 2, because it's squared, we have to include that 2 as a coefficient. So H2 plus Br2 yields 2 HBr, and this is also a balanced equation. So 7.32 asks us to do the same thing. Part A, KEQ equals CH4 methane times H2O water all over CO carbon monoxide times H2 cubed. And so our equation, our chemical equation, we'll start with our reactants on the bottom. It's carbon monoxide plus 3 hydrogen gas because of this 3 in the exponent yields methane, CH4, plus water. And If we look at this equation again, it should be balanced. One carbon, one oxygen, and 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4, 5, 6 hydrogens. So yes, this is a balanced equation. Let's look at part B. KEQ equals SO3 squared over O2 times SO2 squared. So we'll begin with our reactants on the bottom. O2 plus 2 SO2. That's because of this exponent 2. It becomes this coefficient 2. In equilibrium with 2, again because of this exponent 2, SO3. And then we check that this is balanced. We have 1, 2, 3, 4 oxygens. Six oxygens. 1, 2, 3, 4, 5, 6 on our left side, and 1, 2, 3, 4, 5, 6 oxygens on our right, and 1, 2 sulfurs, 1, 2 sulfurs. So yes, this is a balanced equation. Okay. So 7.33, the KEQ for the reaction below has a value of 4.2 times 10 to the negative fourth. So here's the reaction. Methylamine CH3NH2 aqueous plus H2O liquid yields methylammonium CH3NH3 plus aqueous plus hydroxide ion aqueous. And so part A is to write the equilibrium constant expression for this reaction. So KEQ equals products over reactants, and so our products would be CH3NH3 plus multiplied by OH minus all over CH3NH2. Again, water is acting as a solvent in this reaction, and so the concentration of water does not get included into our KEQ equation. So part B is, which are there more of at equilibrium, products or reactants? Well, remember, our KEQ for this reaction has a value of 4.2 times 10 to the negative fourth. So 4.2 times 10 to the negative fourth is less than 1. And so if it's less than 1, then our reactants must be in greater concentration than our products. And so there are more reactants at equilibrium, because we're dividing a smaller number by a larger number to produce this KEQ of less than 1. So 7.34, when steam is passed over coal and allowed to come to equilibrium at 800 degrees Celsius, the equilibrium constant has a value of 8.1 times 10 to the negative squared. And the reaction is carbon, solid, plus water, gas, because it's steam, yields carbon monoxide, gas, plus H2, gas. And so part A asks us to explain why the concentration of water appears in the equilibrium constant expression for this reaction when it is often omitted. Well, in this case, water is a reactant, but is not a solvent. Remember, we don't include the concentration of solvents in our equilibrium constant, but in this case, water is not a solvent. It is a gas, steam, that we're reacting with solid carbon. And so because it's not a solvent in this case, it is included in the reaction. So part B, write the equilibrium constant expression for the reaction. KEQ equals carbon monoxide gas times hydrogen gas all over H2O gas. So this is the formula for the KEQ for this reaction. And then part C, which are there more of at equilibrium, reactants or products? So again, our KEQ is equal to 8.1 times 10 to the negative 2. So 8.1 times 10 to the negative 2 is less than 1. So again, we must have more reactants than we have products. Because if we had more products, it would be greater than 1. So 7.35 for each reaction which is greater at equilibrium. Concentration of products or reactants. So for part A, we have the reaction between HPO4 2 minus plus cyanide ion to yield phosphate ion plus HCN, hydrogen cyanide. We're also told that the KEQ equals 8.6 times 10 to the negative 4th. So we don't actually need to know what this equation is at all. We only need to know the KEQ. This KEQ is less than 1, so there must be more reactants. For the part B, our equation is H3PO4 plus cyanide ion yields H2PO4 minus plus HCN, hydrogen cyanide, and our KEQ is equal to 1.5 times 10 to the 7th. Now in this case, that 1.5 times 10 to the 7th is greater than 1, so we must have more products. So this reaction will generally move in the forward direction. The previous reaction will move in the reverse direction, and we can tell that simply based on the value of KEQ. We don't need to know anything about the chemical equation itself. We just need to know KEQ. Is it greater than 1 or is it less than 1? So 7.36 essentially asks us to do the same thing with different reactions. Part A, hydrogen fluoride plus bicarbonate to yield fluoride plus carbonic acid with a KEQ of 1.5 times 10 to the 3rd. Again, this is greater than 1, and so because it's greater than 1, there must be more products. In part B, NH4 plus ammonium plus HCO3 minus bicarbonate yields NH3 ammonia plus H2CO3 carbonic acid. Our KEQ equals 1.5 times 10 to the negative 3, which is less than 1, so we must have more reactants. So that's the questions from section 7.3 on equilibrium.